Hello everybody. In this video we'll be going over one of the sections in chapter 6 of our text entitled Chemical Composition. Hello everybody. In this video we're going to talk about the empirical formula. Now, whenever I teach the empirical formula, the students at first start to say, this seems like a really kind of odd thing. Like, why are we even care? Why are we learning about this? This doesn't seem useful. So I wanted to put it in your mind in the beginning that the reason we talk about the empirical formula is because we have an experimental technique we've been doing for a long time. I alluded to it in a previous video where we can get the percent composition of each constituent element inside of a compound, and then we can use that to figure out what the chemical formula of that compound is. But we can't really use it to figure out the direct molecular formula. We can only use it to figure out the empirical formula. So before we do those problems, it's important to understand what the empirical formula is. And I think it really helps for people to wrap their minds around the problems that come when we get those mass composition problems, to first understand the empirical formula, because they're really some of the most difficult problems we're going to do in this course. So let's first talk about what the empirical formula is. So the empirical formula is the simplest whole number ratio of atoms in a molecule. Okay. It can be determined from the percent composition or by combining masses. So basically knowing what the mass of each thing is, each constituent element. The molecular formula is some multiple of the empirical formula. And so basically what we can do, this is going to look like a solution map for a lot of these, is given the percentages of each of the constituent elements, we can assume a base of 100 grams. We could find out what the mass of each one of these would be. Then we can use their molar masses to figure out how many moles of each one we would have. And then based on that, we can figure out the ratio between them, which is ultimately going to allow us to determine their empirical formula. So let's look at some examples of empirical formulas. If you had hydrogen peroxide, it's got 2 hydrogens and 2 oxygens. Its molecular formula would be H2O2. But we can divide both of these subscripts evenly by 2. And so its empirical formula would just be HO. Okay? And if you think about this, it has a certain amount of symmetry that goes right through here. So it's just half of the molecule because we divided it both by 2. Benzene, for instance, has a molecular formula of C6H6. Its empirical formula, because we could divide both these evenly by 6, it's just going to be CH. And again, that has to do with this symmetry that benzene has. Okay, you can see that it has this radial symmetry. So just one unit, a CH, spread out along a circle and repeated 6 times, gives us a benzene ring. Glucose has a molecular formula of C6H12O6. These can all be evenly divided by 6. And this time we get an empirical formula of CH2O. And it's difficult to see exactly where we're going to get that. We'd have to decompose that a little bit more. But now we're getting into a more complex molecule. So let's try a little practice problem and see if we can get the empirical formula of benzopyrene from, that is C20H12, from its molecular formula here. So the first thing we need to do is find the greatest common factor, GCF, of the 2 subscripts. This is something you likely learned before, but you might have forgotten a little bit. So let's think about how we go about doing this. First, we take the factors of 20. Okay, so 10 times 2 is 20, and 5 times 4 is 20. There aren't any other combinations that we can use to make up 20 that are whole numbers. Then we look at the factors of 12. 6 times 2 is 12, and 4 times 3 is 12. There aren't any other combinations we can use to make up 12, at least if we're restricting ourselves to whole numbers. Now we need to look at these numbers. 10, 2, 5, and 4, 6, 2, 4, and 3. We need to find the ones that are first common among the two. Okay? So they don't both have a 10 anywhere. They don't both have a 5 anywhere. There's not a 6 up here. And there's not a 3 up here. But there's a 2 here, and there's a 2 here, and there's a 4 here, and a 4 here. That brings us to the first word here, greatest. So, because 4 is larger than 2, our greatest common factor between the two is going to be 4. Now what we do is we're going to go and divide each of these subscripts by the GCF to get the empirical formula. So if we have C20, H12, what we're going to do is divide each of these by 4. So 20 divided by 4 is 5. We saw that here. And 12 divided by 4 is 3. We saw that there. This gives us the empirical formula of C5H3. So I'm going to go through here, and I'm going to give you a step-by-step list of how to get the empirical formula when given percent composition data. This might not make a ton of sense right away, but we're going to do a problem right after it, and I think it's going to make it a little bit more clear. So the first step we're going to do is convert the percentages to grams, okay? Sometimes we might be given the masses directly, in which case we don't have to worry about the percentages. Next, we're going to convert those grams to moles. For this, we're going to need to use the molar mass of each of the elements that we'll look up in the periodic table. Then we're going to write a pseudo formula, so kind of a fake formula using the moles as subscripts. This is going to look a little weird, but I don't want you guys to let it sway you. Then we're going to divide each of the subscripts by the smallest number, by the smallest subscript basically, which will be the smallest number of moles because we're using the moles as subscripts. Finally, we'll multiply all the mole ratios by a number to make all the whole numbers, to make them all whole numbers. We'll only do this if it's necessary. And it helps here, and I think you'll see, to recognize basically the fractions. Okay, so if you have 0.5, that's a half. If you have 0.33, that's a third. 0.67 is 2/3. And obviously, if we already have whole numbers, we want to leave them alone. So let's try one of these problems and see if we can do it. So, in this problem, a laboratory analysis of aspirin determined the following mass percent compositions. Find the empirical formula. So basically this is telling us that if we have aspirin, 60% of it is carbon, 4.48% of it is hydrogen, and 35.53% of it is oxygen. Now here's an example where if we added these all up, we wouldn't get exactly 100%. We'd get 100.1%. So I don't want you guys to let that sway you. Sometimes due to rounding, these just get a little messed up. So you kind of just have to roll with it. So we start by writing down what we're given. And we make the assumption here, we learned in the video about mass percentage, that if we have 100 grams, what this percentage is telling us is that out of that 100 grams, 60 grams of it would be carbon, 4.48 grams of it would be hydrogen, and 35.53 grams of it would be oxygen. Now, it's good to keep in mind that the empirical formula is going to have some form like this, right? You're going to have carbon, some subscript, hydrogen, some subscript, and oxygen, some subscript, because these are the elements that are inside of this compound. We'll need these conversion factors in order to convert all of our masses to moles. And again, we're looking these up in the periodic table. Now we can take a look at our solution map that we've gathered together all the conversion factors we're going to need and converted our percentages over to masses. So we're starting with these masses. We're going to convert them all to moles. That information is all going to get gathered together in what we call our pseudo formula. And then we're going to adjust those subscripts to give us whole numbers and eventually arrive at the empirical formula. Let's see what that looks like. So we start by calculating the moles of each of the elements. So we're going to take the grams of carbon. We're going to divide it by 12.01 grams for every 1 mole. And this will be how many moles of carbon we have in our aspirin. We repeat this for each of the elements, dividing each one, multiplying each one by 1 mole for every however many grams it is, right? Essentially dividing by their molar mass. Now we write our pseudo formula, and I understand that this looks kind of ridiculous. We've been told throughout the entire thing that we can't have fractions of atoms. So our challenge here is to really get rid of these fractions, right? And just in case you didn't pick up on it, these are the values that we just calculated for carbon, hydrogen, and oxygen. So I'm giving you a procedure here for how you're going to get rid of these fractions. The first thing to do is divide each of them by the smallest one. So out of these, our smallest one is 2.21. We're going to divide them all by 2.21. And when we do that, we wind up getting some pretty nice round values here. You're always going to wind up with one that will be 1. And then you're going to have these other pretty nice values. Now, I realize 4.44 divided by 2.22 is not exactly 2. But it's very, very close. And when you're doing these kind of problems, you just kind of have to suspend your disbelief a little bit. And if you get a number that's very, very close, like say it's varying only in the 100th position or something, you just go ahead and write that guy. Here, we get 2.25-ish. And that's just a little too large of a fraction to ignore. So we have to write down 2.25. And we're going to have to go to the next step, where we multiply all these subscripts by some value to make them whole numbers. It's a little tricky to think about what it would be sometimes. So sometimes I like to think about this like money. So if I had $2.25, means I have $2.25. So this is 2.25. So it's pretty clear now that if you multiply this by 4, you'll get a whole value. So that's exactly what we'll do. If we multiply all the subscripts by 4, we get C9H8O4. Now, if we back up here for a second, I want to make it clear to you guys that I gave you a prescription from starting with those weird fractional subscripts that we got by calculating the number of moles of each element that we had based on their mass, and to get to these whole values. I just want to point out that you don't have to follow exactly as I did. It's just a methodology for getting it to work out. The only thing that's really important is that every time you multiply the subscripts, you multiply all of them by the same number. In that way, you're always going to maintain the same ratio between them, and you can do whatever you want, just so long as you wind up with whole values that are the least, that follow, that have no common factors, right? Because that's what we were doing before when we were moving from the molecular formula to the empirical formula. Let's try one more. So if we have a 3.24 gram sample of titanium and it reacts with oxygen to form 5.4 grams of metal oxide, what is the formula of the oxide? So now we weren't given percentages. We're being given masses. But really this just makes it a little bit easier for us. Now we just have to figure out of this sample, what portion of this mass is titanium and what portion of this mass is oxygen. And then we'll be already at the second step of our solution guide map. So from the information that we were given in the problem, we know that we had 3.24 grams of titanium and that we formed a compound by adding oxygen, and the final mass of that compound was 5.40 grams. And we know from the law of conservation of mass that the additional mass that we gained was due to the oxygen. So from these two values, we can figure out what the mass of titanium in this compound is, and we can figure out what the mass of oxygen is going to be. It'll just be the difference between this value and this value. Again, it's important right up front to think about what the general form of your empirical formula is going to be. We have a titanium oxide, so it's going to contain titanium and oxygen. We'll need to collect together our needed conversion factors. Again, we're going to the periodic table and we're figuring out what the mass of 1 mole of titanium is and the mass of 1 mole of oxygen. When we look at our solution map, it's just cut off the first part of our problem. We can go directly from the mass of titanium to the moles of titanium and directly from the mass of oxygen to the moles of oxygen. We don't have to worry about the percentages when the problem is presented to us like this. We'll do our calculation, doing the difference between the compound and the titanium to see that we have 2.6 grams of oxygen. And then we can now calculate our moles. So we have the 3.24 grams of titanium that was given to us in the initial problem, and we'll divide it by its molar mass. Remember that we just like to write it so that we can see the units canceling here. And we'll see that we have 0.0677 moles of titanium. We take that 2.16 grams of oxygen that we calculated from the difference of the final compound and the initial titanium, and we'll divide it by its molar mass to figure out how many moles of oxygen we have. Now we can write our pseudo formula. Again, we're not going to let it sway us that this is kind of a weird looking thing. What we're going to do is we're going to just divide by this smallest value here. When we do that, we see that this one works out really nice right off the bat. We get a 1, as we always will, for titanium, and we get a 2 for oxygen. And we don't have to multiply this by any other value. We already have whole numbers.